our next speaker is Katja Fruold from Germany. Gonna talk about cross-limited timber, CLT, made from oil palm wood. Elaeis Guineensis Jacq.
Thank you very much for the introduction. I'm working at Ostwestfalen-Lippe University of Applied Sciences and Arts, which is very difficult to pronounce, I know. And since 2014, we are working with coconut palm wood, and since 2015, my working group is dealing with oil palm wood. Most projects were in close cooperation with the industry. Today, unfortunately, the results for the CLT are not ready right now. So today I will present the glue-laminated timber, which we tested earlier, and which are finished now, the investigations. So I will present the glue-laminated timber made from oil palm wood today. Over the last 2 days, we already heard so much interesting information on current and future availability of palm wood, why we should use the palm wood and its anatomical structure, that I would like to jump in with the elastomechanical properties of oil palm wood. The properties are varying extremely compared to common wood species. Without grading, according to relevant product properties, the 5th percentile, for example, of the strength would be very low. Too low for market competitive products. Therefore, grading is without alternative. All elastomechanical properties depend on the height within the trunk, because the cells at the bottom are much older than those on the top. The cell wall thickening during the lifetime of the cells results in better properties. Therefore, older palms have better properties at the same position than younger palms. And the position within the cross-section at a certain trunk height has an influence on the mechanical properties as well. This is because of the number of the vascular bundles per unit area. Therefore, the density and the elastomechanical properties are rising from the center to the periphery of the cross-section. But without knowing the age of the palm and the position along the height, the number of vascular bundles per square unit is not a sufficient grading criteria. And of course, the density is much easier to determine. The material properties of oil palm wood are very challenging, but good for many uses. Within the context of a research project, we tested glue-lam lamellae in tension parallel to the vascular bundles. We produced and tested combined glue-laminated timber from density-graded oil palm wood in banding and compression, parallel and perpendicular to the vascular bundles. Because of the property gradient within the cross-sections, the peripheral boards show a great property variation within one board. The diagram shows on the y-axis the density profile over a 160 millimeter wide board, and on the x-axis, and the width is on the x-axis. Directly under the cortex, the density is around 800 kilogram per cubic meter, which decreases very steep within the first 4 centimeter to 300 to 350 kilogram per cubic meter in the board center. The outer 20 millimeter on the right section and on the right side and the cortex are missing. In this example, we produce glue-lam lamellas of 50 millimeter width, which is very small for glue-lam production. On the left, the 50 millimeter lamellas are cut from the periphery only according to their geometry. So the lamella A would have a density gradient from 800 kilogram per cubic meter on the left edge with a tensile strength of about 35 megapascal. And on the right edge, it would have 350 kilogram per cubic meter with a tensile strength of about 7 to 8 megapascal, so less than 1/5. This lamella is far away from a homogeneous lamella. On the right, the same lamella is ripped according to the density profile in stripes with an individual width and homogeneous density. In our case, we produced 4 density classes A to D. The widths result from the set density limit values. For lamellar production, the stripes are edge glued and cut to a width of 50 millimeter. Depending on the limit values of the density, the ripped and the glued lamellas have more or less homogeneous properties. As more density classes, as more homogeneous the lamellas. I won't focus so much on the determination of the density, so we did it with X-ray absorption rate using the DanceLab X from electronic wood systems. And we gave them a special calibration and raw data filtering. On the peripheral boards from the first trunk section, the density at 3 meter height is much lower than at 0.5 meter height, and therefore relevant for the ripping. Because no grading standards and no strength class system exists for all palm lumber, the strength grading classes for European wood was used. Because the lowest strength class is C14, the characteristic values for the strength class C10 and C12 were extrapolated. For the calculation of the forecast limits, the statistical correlation model, according to the European standard, was used. So we produced 20 combined beams with different beam setups from 6 lamellas with a height of 102 millimeter and a width of 50 millimeter. The same resin was used for gluing the GLT as for the edge gluing. Pressing was done on a modified press commonly used for CLT production. The modulus of rupture and the local and the global modulus of elasticity were determined in a 4-point bending test according to European standard. And after the bending test, 2 types of compression test specimen parallel to the vascular bundles were cut from both ends of the bending specimens. The large specimens were taken over the entire cross-section of 6 lamellas, and small specimens with 2 lamellas were taken from the compression and from the tension zones. Altogether, we had 41 large specimens and 150 small specimens for the compression test parallel to the vascular bundles. For the compression test perpendicular to the vascular bundles, we produced extra specimens with a height of 204 millimeter, width of 100 millimeter, and length of 250 millimeters out of 12 lamellas. You see the arrangement of the lamellas on the right. The compression tests were carried out according to the European standard. The tension test on the glue lamellas parallel to the vascular bundles was carried out as well according to the European standard, with a free test length of 9 times the width of the lamellas, so 9 multiplied by 50 is 450 millimeter. And the elongation was measured with a long travel extensometer. This figure shows the properties of the all palm wood as a function of the density for the full-size test specimens in red and for small-size defect-free test specimen from another project in black. Independent of the specimen size, all palm wood shows a higher correlation to the density compared to dicotyledones. This is caused by the much larger density range for all palm wood, and this results in a larger density range of the property larger range of the property values. All strength and stiffness values of the full-size specimens parallel to the vascular bundles increase with the density by power law relationship with similar exponents, except of the bending specimens, which might be due to a comparable low number of test specimens and a very low density range because of the combined GLT. And the properties from compression test perpendicular to the vascular bundles are constant, which might be as well due to the quite low number of test specimens and the low density range as well. The exponents correspond to the results for all palm wood on small test specimens. In contrast to common wood species, the strength of the full-size test specimen in the left figure is above them of the small-sized for the compression strength perpendicular to the vascular bundles is in the same range. The large and the small-sized test specimen for the tension strength parallel and the bending strength are slightly below for the compression strength parallel to the vascular bundles. So the size does not influence the strength values because the elastomechanical properties depend on the anatomical structure at the microscopic level. Main influencing factors are the density, but also the age of the palm, the location within the trunk, so the height and the cross-section, and probably the oil palm subspecies, differences between individual palms and plantation sites. For the full-size test specimens, the compressive strength to the vascular bundles is only about 1.2 times the tensile strength parallel, which is much higher, much lower compared to a low-grade softwood. There we have 2.2 times. The bending strength is about 1.7 times the tensile strength, which is in the range of low-grade softwood. There we have 1.9. And similarly, the ratio of the compression strength parallel to perpendicular is rising from 2.7 to 32.6 times is the compression strength parallel above that of perpendicular direction. And this is much higher compared to low-grade softwood, where we have 8.0. In the figure on the left, the reduction factors for the height and the length are taken into account. The bending strength of the rib beams is higher than that of the non-rib beams at the same density. The characteristic bending strength of the rib beam C14 is 21 megapascal and comparable to that of the C10 beams with 20 megapascal. The difference in the characteristic bending strength of the non-rib C10 beams with 11 megapascal and C14 beams with 16 megapascals is higher. The oil palm wood C10 and C14 achieve the target MOR values according to the standard. The rib beams show a much higher mean local MOE than the non-rib beams, and the C14 are higher than the C10. But the target MOE for this 14 is far from achieving because we have to have 7 gigapascal, whereas the target density is achieved. Because of the power law relationship between strength, respectively stiffness and density, the performance indices we calculated, they are comparable for the strength, but much lower for the modulus of elasticity. Due to the elastomechanical properties, medium and high density oil palm wood can be used for load-bearing purposes, like GLD, but the elastomechanical properties are slightly lower compared to common wood species. Especially we have the problem with the comparatively low stiffness of the oil palm wood compared to common wood species. The high variation of the oil palm wood's properties require grading, for example, according to the density. The strength grading according to the density and the defined density limit values in the study are reasonable in principle. Designing beams with lamellar positions according to their density has a significant influence on the properties. Ripping boards according to their density into stripes and edge gluing these stripes to density homogeneous lamellas results in higher MOR and MOE values. As the oil palm wood is different in structure and properties compared to common wood species, special product development, including material and product modeling, and process development is necessary to achieve market competitiveness. One of my PhD students modeled the bending properties using finite element method for future optimization. Standards for common wood species do not automatically apply for all palm wood. Therefore, the building codes need to be adapted for all palm wood. Many thanks for listening and for the research funding, our partners for their help, and all my students for their lab work. Many thanks.
Thank you for your presentation. Any question?
Thank you very much for your interesting presentation. I just have a doubt of how do you measure the mechanical tests taking into consideration the moisture content inside the wood. How do you manage to do this? Because I think the moisture content can affect the final properties, final mechanical properties. So
Yes.
how do you do this?
Yeah. Thank you very much for this question. I didn't mention that we did kiln drying for all our lumber, so we did technical drying to about 12%, and then we put it in 20 degrees, 65% relative humidity in the climate chamber, which is according to the European standards, and then we tested it according to at the around 12% moisture content. So all results are at 12% moisture content. And this we checked after the testing as well. More questions?
Yeah.
So we didn't test at any other moisture contents till now. Sorry for that.
Okay, let's thank our
Thank
speaker
you.
again. Okay, our